to do is just talk a little bit about, or do a couple of practice problems related to density. We'll talk a little bit about how density determines buoyancy, and how temperature affects density, and so as you guys said in your question today, Ali told us the formula for determining the density of an object is take its mass and divide it by its volume. So the formula for density is mass divided by volume. So we need to determine if we have the actual objects in our hand, we just need to follow our usual steps that we've already learned to figure out the mass of the object, to figure out the volume of the object, and then plug the mass and volume into our formula to determine the density. So here's an example. I have a cylinder with these dimensions and these measurements. So to calculate its density, first, I need to calculate the volume. Go ahead and do that on your own paper for a second. Figure out the volume of this cylinder. All right, so what are my steps to find the volume? What do I have to do first? I always want you to do this when we're solving a problem. Sean?
You have to write the formula.
Yep, which is what for this?
Volume equals pi times radius squared times height.
Correct. Oop, don't. My second step? Colin? Substitute your numbers, and then finally, calculate and give an answer. What, Kazia? With units. And if we do that, we get an answer of 49.5 cubic centimeters. Okay, I already know its mass because it was given to you. How might we have measured that mass? Probably on a triple beam balance. So if I take my formula, density equals mass divided by volume, divide 519.75 grams by 49.5 cubic centimeters, we get an answer of 10.5 grams per cubic centimeter. Who could tell me the answer to this question? What is this cylinder made out of? I don't know, is it?
Is it?
Who knows? Tyler? Silver, how do you know?
Because silver's density is the same.
Okay, so if we look at our chart that we have, which helps us identify the density of different properties. Okay, if we look up silver, what's its density, Tyler, on the chart?
10.5.
10.5 grams per cubic centimeter. So this is probably silver. Because we know density is an identifying property. Density can help us figure out an unknown substance because all pure silver has the same density at a given time. Ed?
The sheet you're talking about.
You need one?
Yeah.
All right. You go ahead and solve this problem. You done, John? Oh, one of these as well? Jake, did you get one of these? I gave everybody one class. What's your reminder? Medicine. All right, how am I going to do this? What do I need first? Jenna,
Find the volume.
what's that?
To find the
To
volume.
find the volume. So how do I do that with this object? Continues in
15 times 5 times
Yes, I multiply length times width times height. Okay, 6 times 5 times 15. And I get 100 and, what is that? 450. What? Waffle patties? Centimeters cubed. All right. The mass has been given as 770 grams. So what's the density of this box in column?
1.79 grams per cubic centimeter.
Do our math, 1.7 grams per cubic centimeter. Does anyone know what metal this is? Alex? Magnesium.
Yeah, look at that.
Magnesium has a density of 1.7 grams per cubic centimeter. Now, we mentioned this yesterday, that heat can affect the density. As we heat a substance, the molecules spread out. The volume of a substance gets larger. And so how does that change its density? Jack? So how does expanding volume change an object's density, Tyler? It does. Imagine the formula. Mass divided by volume. When you heat something up, do you change its mass?
No.
No. But if it expands, are you changing its volume?
Yes.
So what happens to its density, Ella? It decreases. The molecules are less compact. They're more spread out as you heat up the substance. So it does affect density. Volume increases, mass remains the same, and therefore the density decreases. All right, there's the chart in your table, so you see. And when we do a lab this week, you're going to be measuring some unknown objects, and you're going to have to identify them. And so you're going to use the chart like this. Now, buoyancy, the ability of an object to float in a solid, in a liquid or a gas, is dependent on density. So buoyancy is the force that keeps something afloat. And not only does density determine whether or not an object floats, but it also determines how high or how low it floats. So if we put a piece of wood in a beaker of water. All right, look at this piece of wood in the water first. Is it floating? Yes. And now look at this piece of wood. Floating?
Yeah.
Can you tell me anything about the density of these two pieces of wood? Abby?
The first one that you put in seems denser than the second.
Okay.
Because it sounds further.
Do we know anything about the actual measure? What is the density of this piece of wood? Could you?
Drop it on the ground, yes.
drop it on the ground and then pick it up? Yes, I can. Could you give me an estimate of the density of this piece of wood? I think you could. I think if somebody in this room thinks really hard, they could probably give me an estimate of this chunk of wood plus or minus 0.2 grams per cubic centimeter. Sean?
0.4 grams per cubic centimeter.
Probably not. So that's off by a fair amount. Anyone have another idea? Ali?
0.5 grams.
No, I said it's off quite a bit. So don't look this up. Use other means of trying to figure it out, besides looking on the chart. Because this type of wood is not on your chart. Colin?
0.91879247
Why do you say that?
Because, well, the reason I said 9 is because it floats, but almost, I would say about 90% of it's submerged.
Okay. So this is what I was hoping you would arrive at. So not only, so we know it's definitely less than what?
Water.
Water. And the water, the density of water is 1. So we know it's got to be less than 1. Why do I know it's not 0.4 or 0.5? What would an object with a density of 0.4 or 0.5 look like when I put it in water? What? No, not if it was 0.4 or 5. Sienna? It would be like this piece of wood. This piece of wood, when I put it in the water, it looks to me, not quite, but close enough, that about half of the wood is above the surface, half of the wood is below the surface. That gives me an indication it's probably around 0.5. 50% of it's above the surface, 50% is below. This piece of wood is about 90% below the surface and only about maybe 10 or 15% above the surface. Probably its density is about 0.85 to 0.90, somewhere in that vicinity. Okay. Tell me what's the density of this cube. Now, you can only tell me one thing probably. It's more than 1. More than 1. So we can estimate the density not just based on whether or not it floats, but how high and how low in the water it floats. So liquids and gases with different densities separate out. If I were to take a bit of this Yoda tears and I were to add to it some water,
Joy in its most pure form.
just let this sit for a moment or two,
You said that it was really hard to find.
okay? What we'll see,
He's got more. He's got a Yoda in him.
I probably should have done this a little differently. Alright, let's see if I can do this on the fly. I should have set this up in advance, but I did not.
There was a. Is that hydrogen peroxide?
Nope.
What's that? Is it hydrogen?
So,
I was gonna say,
if I take a few different liquids,
nothing like sugar juice.
alright, so if I take some of this corn syrup,
Oh, yeah.
alright guys,
Ali.
alright, Now let me get some Yoda here.
They'll kick them. They're floating. It's because one is less than. It's like the oil and water. That's how about that. Be careful, Mr. Beautiful layers. Or like sex. Oh my god. They're layers.
So these substances, who could make an inference about the density of these three substances that I just added to this graduated zone? Alice? Okay. Anything else, Abby?
The Yoda tears are the least dense.
Yoda tears are the least dense. One more, Ellie?
You use the less amount every time you add a new.
Okay, that was just sort of by happenstance. I could have done that, but that is correct. All right, so because I have these three liquids, and each of them are a different substance, they each have different densities, and therefore they separate out. The least dense is the one on top, the most dense is the one in the middle, on the bottom, and then the middle one is in between their density. So liquids and gases separate out with different densities. Less dense objects float in more dense objects. This picture here, this gentleman is doing something that's pretty dangerous, but he is sitting in a pool of liquid mercury, and he's floating. So that is not, he's not sitting on like a solid, that is liquid. Look on your chart. Tell me about mercury. Tell me something about mercury from your chart. Niksha?
It has a high density.
How high?
13.
Has an extremely high density. The density of mercury is 13.6. Okay? That means a piece of lead will float in mercury. Okay? If you ever held like a lead sinker from fishing, you know it's very dense. Okay? Silver, nickel, copper, all those things would float in mercury. Now, mercury is a toxic heavy metal. It's bad for you to inhale it. So we don't really use it. We used to use it in school back a long time ago. You can hold it in your hand and it rolls around like it like stays together. It's a metal. It is a metal, but it's a liquid metal at room temperature. And so, yeah, I think it is similar. Gallium is another very dense.
Except it's way less dense.
Yeah. So I'll show you. This is a cannonball.
Because the Torricelli experiment is portable. And it's portable because the mercury column is short. Why is it short? Because mercury is a very dense liquid. A liquid so dense that cannonballs float in it.
That's like a lead ball floating in this liquid. So,
Because the Torricelli experiment is portable. And
all right.
it's portable because
So again, if you were to add several things, this is what would happen. You know, you could put solid objects in this column of different substances, and depending on their density, some would sink, some would float, and you can infer their density based upon which level they float. You guys seen this movie? Great movie. All right, just watch for a minute. If you've not seen it, definitely you should see it. It's really cool. But I want you to have in mind what we've just talked about as we watch this scene from, what's the name of the movie? Raiders of the Lost Ark, really. It's the first Indiana Jones movie. So just watch. All right, shh.
There's nothing to fear here. Scares me. Sí, señor. Adiós, señor.
Are you ready for the world's slowest closing door?
Letting us look in your eye.
Want to see what happens next? You have to watch the whole movie.
I know what it is. It's obvious.
So, here's my question. What did he do wrong? So, if you think about what we're talking about, what was the problem with the Indiana Jones did? Jake?
You put something on the thing to replace it that wasn't the same density.
Yeah, so what do you think the idol was probably made out of? Gold. What do you know about the density of gold?
Very high.
It's really high. Yeah, it's very dense. So do you think a bag of sand, the size that he replaced it with, do you think their masses are even close? No. I'm going to estimate the quantities here and give you a problem one of these days to have you figure out, well, how much sand would he have needed to replace it with to equal the mass? What did he seem to be trying to match? Well, the volume, right? The size of the bag he had of sand was about maybe similar to the size of the idol. And so it looked more like he's trying to replace the volume of gold with the volume of sand, which is probably not what the right decision was.
I just wanted to say I found a different thing he did wrong. It's not necessarily related to science, but
Okay?
but wouldn't it have been simpler because the boulder was rolling down from up high along like a certain thing? Wouldn't it have been easier to run under
Towards
where
it,
it was
yeah.
running from? If he had run under it before it
But then
reached
it's
the
going to
ground.
block his exit of the cave.
Well, no, he could just go behind the boulder.
Yeah, but then he's going to be stuck in the cave.
That's what I was talking about.
All right, so anyway, that's our notes. So let's